Good morning dear students. In the previous classes we discussed about the static and dynamic characteristics of measuring system and basic measuring system. In this class we discussed about the errors in measuring system. So already we discussed about the classification. So the classifications of errors is, there are three types. The first one is graph error, second one is systematic error, and third one is random errors. And we know that the graph errors can occur only because of human mistakes. The second one, systematic errors, and these can happen due to the systematic errors means the instrumental errors, and the third one is random errors. So we know that the random errors occur because of environmental disturbances. How these errors will occur, we don't know. So we have to take some probability steps so that we can avoid this type of random errors. So in that, the first one is graph error. So what might be the definition of graph error? So the definition of graph error is the errors those done by the experimenter can be called as graph errors. So the errors those are only done by the experimenter, not because of the instrument. So the experimenter, if experimenter make any mistake, because of that it makes some errors, so that errors can be called as graph errors. So this class of errors mainly occurs human mistakes in reading, recording and calculating the measuring results. So mainly occurs because of in reading, recording and calculating. In hurry, so many times in reading we can jumble the words, otherwise we can replace the words, and recording, while recording, as well as calculations, we can make some mistakes in formulas. So likewise these errors can be occurred. So this type of errors can be called as graph errors. These errors commonly occurs with the misreading of the following numbers with one by another. So see that 1 and 7, 3 and 8, 6 and 9. Sometimes in hurry we can able to tell 1 as 7, otherwise 7 as 1. Sometimes 3 as 8, 8 as 3. So likewise 6 as 9, 9 and 6. So this is the way in hurry you can able to tell the reverse numbers. That means 1, 7 are looking also similar. So in hurry you can able to tell 1 as 7, 7 as 1, likewise 3 as 8, 8 as 3, and 6 as 9 and 9 as 6. So this is the example here given. So 27.3 can be read as 27.8 or 21.3. So here 3 can be replaced with 8 or 1 can be replaced with 7. 7 can be replaced with 1. So likewise this type of mistakes can be occurred. So sometimes we can jumble the numbers. So see, this is the example for jumbling. Sometimes the errors occurs due to jumble reading of experimenter in hurry. So that means numbers we can jumble. So that means 23.2 can be 32.2. So otherwise 22.3. So likewise. So these type of errors can be called as graph errors. So if you can able to make any error, we have to avoid this type of errors. So why? Because graph errors can not have any mathematical solutions. So once we did means we have to that means what is that? We have to accept that readings. So we don't know when it was happened, and we don't know how to rectify it. So we need to accept it. So that we need to take care of this type of errors. So while reading, we need to read the manuals as well as for the calculations. So in the calculations part, we need the manuals, as well as we need to take care very much while reading. So otherwise we need to do so many times. So the same reading for so many times. So likewise we can avoid this type of errors. So these errors may be any amount. There is no mathematical analysis available as a solution. It is impossible to identify them. So if you can take 100 errors, we don't know at what error we can make error, like graph error. So we have to avoid such type of errors by taking care only. So these can be avoided. So if you want to know some error, So after the final conclusion, we need to write how to avoid those errors. So these are the ways to avoid these errors. So they can be avoided by the following precautions. The first one, great care should be taken in reading and recording the data. So the great care must be taken while reading. So we have to focus on this scale only, then only we can read carefully. 2, 3 or even more readings should be taken. For the same measurement, we need to take 2 or 3. Then we can able to conclude what is the best value for that. So this is the way we can able to avoid this type of errors. Some readings must be taken by different observers. So we need not to depend on the same observer. Of course, we need to take another observer. So after taking the different observers' readings, we can able to conclude which one is the best reading. And here see that we must not stand on one observer's reading. Suppose maybe one observer he will well take care of while recording the errors, but sometimes he may also do the mistakes. So at that time we must not stand on only one observer's reading. We need to observe the readings of many observers side by side for getting the best results of measurements. So we have to collect the different observers' readings so that we have to place them side by side, so that only you can able to get the best results. So we cannot stand on only one of the errors. So these type of readings, this type of errors can be called as graph errors. So these errors only occur because of human mistakes. That means not because of instruments. The second one is systematic errors. So these systematic errors, what is the definition? So before going to the definition, there will be 3 classifications in this. The classification, the first one is instrumental errors, second one environmental errors, third one observational errors. So you must have a doubt here. So instrumental error, okay, it is also systematic error which can be done by system. Environmental errors, of course, if the reading is changing by temperature, it is also system mistake. Observational error. So mostly the observational errors can caused by the humans. So this third one must be under graph errors. Why? Because it was here. Let us take a analog ammeter. So most common problem is parallax error. So analog ammeter and take a digital ammeter. So digital ammeter must if you can connect the analog ammeter, there will be parallax error. But here there was no parallax error. So that means this parallax error occurred by the instrument only. What is that instrument? Analog instrument. But it was not showing by the digital instrument. So this error also will come under systematic errors. So I think you got the point. Okay. So the parallax error generally made by the humans, but it was occurred because of the analog instrument, not because of the digital instrument. If there was a digital instrument, there will be no observational error. So that will come under systematic error. So these are the main 3 classifications in the systematic errors. So we can see the first one, instrumental errors. So this is also had the classification. So why these errors will occur? The first one, due to inherent shortcomings in the instrument. Inherent shortcomings means large frictional elements like springs, all those things. So we can discuss that in detail. So due to misuse of instrument, maybe a well calibrated instrument cannot able to read an accurate or precise results with a unknown user. So due to the misuse of instrument. So the next one, due to the loading effects, if you cannot able to connect the proper loads, the instrument also may errors. So this type of classification can be called as due to loading errors of the instrument. So these are three types can cause to occur instrumental errors. In that the first one is inherent shortcomings of instrument. So what is the definition? The statistical errors, those occur due to their mechanical structure. I already told you, so spring large spare parts. Because of these only, these errors will occur. The statistical errors, those occur due to their mechanical structure, are called as inherent shortcomings of the instrument. So these errors may cause the instruments to read high or low values. Sometimes the spring may be very free. So at that time it can able to show high values for a lower values. It will be very free after a long time. So sometimes the spring may stuck. That means if you cannot use that instrument for a long time, it may be stuck due to some dust, otherwise anything. So at that time it can able to show a low value. So these errors may cause the instrument to read high or low values. So if the spring is free, it can able to show high value. If it is stuck by some dust or anything, it can able to show low value. It is possible to reduce these errors to a great extent by using the following methods. What are those following methods? The procedure of the measurement must carefully planned. Substitution methods or calibration against the standards may be used for the purpose. So that means before going to the why the spring is going in that far means, so while taking the instrument, new instrument, analog instrument, we are not following the procedure, initial procedure, so that only after the long time the spring is spring smoothly. So that we need to follow the procedure of the measurement carefully. So substitution methods like calibration against the standards. So we need to, so we all are using the secondary standard instruments in the laboratory. So these secondary standards instruments must be calibrated as per their requirement. So some instruments must be calibrated between 1 month and 1 month. Few of them 6 months, few of them 1 year. So likewise, so in their period we must be calibrate them so that we can avoid such type of errors. So correction factors should be applied after determining these errors. So these can be avoided. That means this point can come under if the instrument is more precise. Suppose if it was always showing some, let us take a voltmeter, if it was always showing 2 volts difference, what we have to make? We have to calculate it for 2 volts less or 2 volts plus. If it was showing 2 volts plus, we have to calculate the coil 2 volts less. So that means it must be precise. Precise means the same distance for all successive operations. So the same 2 volts for all successive operations, so that we can able to calibrate them. So by calibrating them, so we can able to avoid correction factors. These are the correction factors. What is the correction factor here? In this example, 2 volts is the correction factor. Sometimes it may be plus or sometimes it may be minus. So next one, the instrument must be recalibrated carefully. Already we can discuss it. So as per their periods, we have to recalibrate them. So next one is misuse of instruments. What is the definition of misuse of instruments? So definition: the statistical errors, those occurs due to the fault of the operator, can be called as misuse of instrument. This is not because of instrument. This is occurred by the operator. Then you have to ask a question here. It will come under graph errors. So why it won't come under graph errors. Let us look. So the good instrument used in an unintelligent way gives errorsome results. That means if you don't know about the instrument, if you are using that, definitely it will give the errors results. The errors can be reduced by the following methods. Operator should read user manual of the instrument carefully. So before going to the measurement, we need to read the user manual carefully so that we come to know the procedure how to make the measurement, so that only we can able to get the accurate results. So why it will come under instrumental errors, that means systematic errors. So many instruments can be calibrated at the company only. So we need not to calibrate always. If we need to calibrate or recalibrate every time, that must be the instrument fault only, not our fault. Okay. So that means this will come under, this error also will come under instrumental error. So operator should read user manual so that only they will provide some manual to give accurate results. So it won't give accurate results, we cannot follow that manual. Operator need to adjust the instrument to the initial conditions before going to the measurement. So there will be some initial conditions for a particular type of instruments. So for such instruments we need to make some initial adjustments. So like live zero, those things. So operator need to adjust the instrument to live zero. I am telling now. So live zero. So live zero means sometimes the knob will be at some, let us say voltmeter, 3 volts or sometimes at 4 volts. So even if you cannot give any input, it will be there at 2 volts or 3 volts. So that means thereafter we can give, it makes a difference of 2 volts or 3 volts for every input. So what we have to take, we have to make, so there will be certain knob will be there, we can correct that with our screwdriver. So we have to make that knob as 0, so it can be called as live 0. So we have to set that knob as at the 0 position before going to the measurement. So that means this can be called as live 0. By adjusting that, we can able to, so this is also can be called as initial conditions of the instrument. Okay, so by adjusting that as a live 0, we can able to get some good results. So for avoiding this type of misuse of instrument errors, so we have to know the manual of the instrument before, and we need to make the initial adjustments as well as live 0 adjustments. So next one is loading effect. So what might be the definition of loading effect? The statistical errors those occurs due to the improper loads attached to the instrument can be called as loading effects. So these errors can occur if you connected the instrument for the improper loads. So let us take what are those loads. These are the most common errors committed by the beginners. So the beginners can make this type of errors. They can give a well calibrated voltmeter for the improper loads. So at that time we might get the errors. So this type of errors can be called as, can occur due to loading effects. So a high calibrated instrument may give misleading results when it was connected to improper loads. A voltmeter won't give a good result when it was connected to a high resistive load. So we had a problem for this, and by doing that problem we can able to know that how a voltmeter cannot able to read a proper voltage when it was connected to a high resistive load. So you can see that in the problem. So these errors can be reduced by using the following methods. Operator should read user manual of the instrument carefully. So instrument user manual they must need. For which load this type of instrument we have to provide. So we have to connect so that only we can proceed for the measurement. Sometimes by taking the example voltmeter we have certain ranges. So 0 to 20, 20 to 200, 200 to 600, 600 to 1000. So like that it will have certain ranges. If we can able to give a 200 volts for a 0 to 220 range, means what will happen? It cannot able to read. So these can do by the beginners. So that what we have to do, if you know the manual before, we can able to know the knowledge of rotating that knob as per our requirement. Okay, so this is the way you can able to avoid these loading effects errors. So this is the part of systematic errors. So coming to the problem, so this is the problem for loading effects. How a high resistive, if you connect the voltmeter across a high resistive material, how it can able to do the wrong values, we can able to calculate here. So see here, a voltmeter having a sensitivity 1000 ohms per volt. What is meant by sensitivity of a voltmeter? So here you can tell it by the units. So ohms per volt, that means the resistance of the voltmeter per unit volts can be called as sensitivity of that voltmeter. So that means for 1 volt there will be 1000 ohms resistance. So if it have a full scale of 150 volts, then what will be the total resistance of the voltmeter? 1000 ohms into that 150 volts. Why? Because for 1 volt it was having 1000 ohms. So for 150 volts, 150 into 1000 ohms. So this is the way you can able to calculate total resistance of the voltmeter. This will be useful in the problem. So this can be called as sensitivity. Sensitivity means the resistivity of the voltmeter, resistance of the voltmeter per volt. So it was reading 100 volts on its full scale. Full scale means 150 volts scale. So it has the full scale value of 150. That means it can able to calculate the voltage 0 to 150. So when it was connected across an unknown resistor in series with a multimeter. So there is a resistor in series with a multiammeter, sorry, not multiammeter, milliammeter. When the milliammeter reads 5 milliamps, calculate the following. So what we need to calculate here is apparent resistance of the unknown resistor. Sorry, here apparent resistance. So similarly, actual resistance of the unknown resistor. So error due to the loading effect of voltmeter. Error due to the loading effect of voltmeter. So how can I able to solve? So what is meant by apparent resistance of unknown resistor? So the resistance that was calculated by the instrument can be called as apparent resistance. So the actual resistance of that existed resistance can be called as actual resistance, or it also can be called as true resistance. The error between the actual and apparent can be called as error. So first, how can I able to calculate the apparent? So before calculating this, we need to write the given data, so that only you can get some formulas. If you have the given data in front of us, you may have the plan how to calculate the above three. So first write down the given data. So what is the given data? Voltmeter sensitivity is 1000 ohms per volt. Voltmeter reading. So what it reads? Actually 100 volts. This is the actual apparent reading, not actual reading. So by calculating the error only we can able to tell whether it was actual reading or apparent reading. So next one, voltmeter sensitivity, voltmeter reading 100 volts, voltmeter full scale reading 150 volts, milliammeter reading 5 milliamps, and so that I was formed a circuit here. So I was not connected ammeter here, so I just make 5 milliamps. So that means it was showing that 5 milliamps in series with R. So there is a voltmeter. So voltmeter connected across the R. So now our aim is we need to identify the actual resistance of R and apparent resistance of R and the error between the apparent and actual. So we need to calculate R apparent, R actual and error. So first one, to find R apparent, we need to obtain the total resistance of the circuit. So how can we able to calculate the total resistance? We know the current as well as we know the voltmeter reading. so that voltage divided by current will give the total resistance. So total resistance RT is equal to voltage reading divided by current reading, that is equal to 100 by 5 milliamps, which will give 20 kilo ohms. So here in the problem, the resistance of the ohmmeter was not given. So we have to neglect that resistance so that only we can get the total resistance. So if they can give, we need to include that. So if they didn't give, we cannot include that, we have to neglect that. So by neglecting the ammeter resistance, so RT is equal to R apparent. That means there is no other resistance we have here. There are two instruments only. What are those? Ammeter and voltmeter. So now we are only finding the apparent one, not the true one. So when calculating the true one, we need to consider the voltmeter resistance also. So here we are only calculating the apparent resistance. So voltmeter reading by simply current reading. So it will give apparent resistance value. So apparent resistance of the unknown resistor is R apparent, that is equal to 20 kilo ohms over time. So now we have to identify the actual resistance, so that only you can able to identify the error between the instrument reading and true value. So to find the R actual, we need to obtain the resistance of the voltmeter. Now we need to obtain the resistance of voltmeter, so that only we can able to identify the total resistance. That means the voltmeter resistance is in parallel with the actual resistance, so that we can get the total resistance. So before that, voltmeter resistance. How can you able to calculate the voltmeter resistance? We know the sensitivity as well as full scale reading. So sensitivity means the resistance of the voltmeter per unit volt. That means 1 volt. So 150 volts means 150 into sensitivity. So this voltmeter resistance RV is equal to sensitivity into full square, which will give 1000 into 150. So it will become 150 kilo ohms. So this is the resistance of the voltmeter. Now from the circuit, from the above circuit you can see here. So this is the circuit. So R is in parallel with the voltmeter. So the total resistance must be actual resistance into voltmeter resistance divided by actual resistance plus voltmeter resistance. So from the circuit, R apparent is equal to R actual into R voltmeter. So that means voltmeter resistance divided by R actual plus R voltmeter. So now what we need to calculate here, R actual. So we have to take that from to one side, so that we can able to calculate it. So here R apparent, that means the denominator RF plus RV came to the left hand side, so that R apparent into R actual plus RV is equal to the right hand side value. So it will give us this one, R apparent into R actual plus R apparent into RV, that is equal to R actual into RV. So now what we need, R actual, so that the left side R actual part I will take to the right side. So it will be minus. So now I will take R actual common, then what will happen, you can see R actual is equal to RV minus R. So now I want R actual, so R actual is equal to RF into RV divided by RV minus R apparent. So we know these values, RV we know, R apparent we know, so we can substitute those values. 20k into 150k divided by 150k minus 20k, so which will give the R actual 23.077 kilo ohms. What actually the resistance is 23.077, but we calculate that as 20 kilo ohms. So this is the error we identified. So how can you able to calculate the error? So this is the way you can able to calculate the percentage error. Percentage error is equal to measured value minus true value divided by true value into 100. So measured value 20k minus 23.077k divided by 23.077k into 100. So it will give this error, percentage error. So this much of percentage error we got if you connected this So 20 kilo ohms. That means 20 kilo ohms means high resistive. I told you before in the loading effects, if a voltmeter connected across a high resistive load, it may give improper readings. So see here, it was provided minus 13.33 error. So now the same problem I can do with the another parameter. The same sensitivity, but it was read with the 40 volts. But you can see here the ammeter, milliammeter reading is 80 milliamps. There it was 5 milliamps. 5 milliamps means less current flowing, that means high resistance. 80 milliamps means high current is flowing, that means low resistance. Then see the results. If you just make the same value, that is same formula here, you can able to obtain the results. We can see the results. Apparent resistance here it was 50 ohms. That means there is 20 kilo ohms high resistance, 50 ohms very small resistance. So actual was 50.01. So this is the true resistance we need to identify. See the difference, there is not such a big difference here. There it was 20k and 23 point something k. So here it was 50.01, almost negligible. So what is the percentage here? See here minus 0.034%. So that from this example we need to know that if you connected a voltmeter across a high resistance material, it will give a improper voltage. For such cases we need to read manual of the voltmeter, so that only we can proceed. Okay. So this is about the today's class. In the next class we can see about the remaining errors. Thank you, dear students.